Welcome back. And today we're going to start talking about synchronization. It looks like we have enough seats now, so make sure to sit in a seat rather than on the floor. And we'll talk a little bit about the wait list and everything in a moment. So if you remember last time, we actually talked about the thread fork system call or process or whatever you want to call, which is basically something for creating a new thread. And basically, it starts out at user level, as does almost every system. Well, every system call we're going to talk about starts at user level. And what happens when it exits is that you have a new thread that's been placed on the ready queue and is ready to run at whatever point. The arguments are kind of the obvious ones. There's a pointer to the procedure that you want the thread to run. There's a pointer to a list of arguments. And there's also a size of the stack. And we said briefly that the implementation here was sanity check the arguments. That's kind of a debugging thing. Then we enter kernel mode, sanity check them again. That's a security thing. And then we allocate the new stack, the thread control block, initialize the thread control block with just a little bit of initialization, put it on the ready queue, and poof, we're ready. Notice, incidentally, that we don't actually run anything about the new thread. We don't initialize it. We don't start it. All we do is we put it in a mode that we can put it off on the ready queue, and when we get around to running it, then it'll initialize itself. And this is kind of the reason we did this particular strategy, and we'll go through it again, was really to simplify things. Because you can imagine that if the parent thread that's creating a new thread had to somehow go off and start running the new thread, you'd have to switch stacks around. It'd be just kind of messy. So instead what we're doing is we're packaging up a new thread, kind of a proto thread that's ready to run, putting it on the ready queue, and when the scheduler gets around to running it, it'll initialize itself. So it's a much cleaner sort of way to do things. We don't have to worry about which stack we're running on, because we just run on the parent stack, and when we're done we have this little object that's ready to run later. Here was our diagram that we used to describe this process. Here's the thread that's, here is a thread that's been running for a while and it gets around to yielding. And this thread root stub is really that proto thread, if you want to call it. The only work we've done there is we've allocated a TCB, we've allocated a stack, we've put a few registers in the right places, and that's it. We haven't even initialized the stack or done anything. And the act of switching over here basically will initialize the thread. All right, were there any questions on that from last time? No questions? Okay, so this all made sense to everybody when they thought about it? As I'm sure you all thought about it deeply over the weekend, right? Okay. So what does the thread root procedure look like? Well, remember, the thread root stub is really set up to be here. Let's see if we can sit in seats now rather than the aisle, since we've got seats. So if you think about what the thread root stub looks like, we've really set up a return address such that this thread root procedure will start running. This is the procedure. And notice that we basically do some housekeeping at the beginning, which is some statistics. Don't sit on the floor. Try to find a seat. There's still a few. We switch into user mode. Why do we do that? Why should we switch into user mode? Yeah.
You don't want the actual user thread to have kernel mode permissions.
Exactly. If you notice this call here, this is a pseudo C syntax. You've probably seen this before, but we're calling the function with its arguments. And once we start calling this, we are running arbitrary code that was given to us when the thread was created, and we really don't want to do that in kernel mode. So it's very important that we get into user mode before we start running. Now, why were we in kernel mode? We're in kernel mode because we were in kernel mode from switch, which put us into the thread root stub in kernel mode. Okay, so we're in kernel mode when we switch, which is something you're going to want to definitely remember as you start doing your projects. You're in kernel mode at switch. Okay. So now we go to user mode, we run our function, we thread finish, we're done. All right, so that was just, we just executed the thread. Now presumably somewhere while this thing is executing, it executes a yield or gets switched out, and other things will run concurrently with this particular thing. Housekeeping was things like recording start time of thread and so on, statistics. We may talk about that a little bit later. And once the thread root starts running, the thread stack just grows and shrinks, just like a regular procedure. So notice thread root here calls the code there. That's why thread root's this part of the stack, the code's there. Okay, so this is hopefully not surprising to anybody. And then finally, thread finish basically has to trap back into the kernel, clean up some stuff, deallocate the TCB eventually, and we talked a little bit about that detail last time. Can't deallocate something while we're still running on the same stack and so on. Any questions about this? Try not to sit on the floor. Seats over there. No floor sitting. There's a seat down here too, couple seats. Okay. So we then started talking about correctness of systems with multiple threads. Okay, so now we assume we've got threads. What can we do with them? And the most important thing that I kind of was getting on at the end of the lecture, and this is where we're going to pick up, is you got to view the dispatcher-scheduler combination as malicious in some sense. If there is a bug in your code where two threads can behave badly, if they're interleaved in a funny way, the scheduler will find it. Okay, unfortunately, it may find it at 3 in the morning when you haven't been sleeping for 48 hours or something. But you got to assume that if there's a bad interleaving of threads, the scheduler will run across it eventually in some sort of weird bug. And so that was what the topic of today and kind of the next couple of weeks is clearly going to be. And to sort of start this discussion, we kind of talked about an ideal. The ideal was independent threads which have no shared state whatsoever between them. So they're each doing their own thing. And the reason this is a nice ideal to think about is because it doesn't matter what kind of interleaving of threads go on, as long as your OS is not broken, because it doesn't, you'll get the same answer no matter what you do, because the two of them don't depend on each other. Okay, if there's nothing that thread A and thread B do in common, you could start and stop A and B in any arbitrary way, and you'll get the same answer at the end. Okay? That makes sense to everybody? Now, why is this an ideal? Nothing ever operates independently. If nothing else, the two threads are in the same operating system. Two device drivers, or there's a device driver underneath there, maybe for the disk or something that could screw both of them up. So there's always some shared piece here. But barring those kind of bugs, if you have something that's truly independent, that's kind of easy to think about. Unfortunately, you don't get the full power of threads then. You'd like to have sharing going on, and that's where things get interesting, and that's the cooperating thread case. And this is the case where two threads share information, and now suddenly it does matter how they interleave, because if you don't program correctly, you'll get the wrong answer. Okay, and it'll happen at the most inopportune time, and you won't necessarily know why if you haven't been disciplined in your programming style. So as we start talking about synchronization, it's going to be about being disciplined in how you program. So there's spare seats up there. Make sure not to sit on the floor. Several seats throughout. So cooperating threads, they're non-deterministic. They're non-reproducible. All right? You run them twice, and you've programmed them badly, and you get a different answer each time. So that's kind of unfortunate, I would say. And this is often called Heisenbugs. Okay? And I'm hoping that maybe at the beginning we scare you enough into making sure that your threads that are sharing state have been designed cleanly so that that state sharing does not lead to weird answers. Okay? And that's going to be our goal of synchronization. That's the topic of today. Okay. So, any questions on this before we go on? Yeah?
By non-reproducible, do you mean that if they are programmed wrongly, only then they'll be non-reproducible?
So the question is, by non-reproducible, do I only mean if they're programmed incorrectly, you won't get the same answer? If they're programmed correctly, you might get a consistent answer, but then the timing might be inconsistent as well. But yeah, hopefully we're going to be taking a stab at reducing the non-reproducibility by programming them correctly. There's still some ways in which it can be non-reproducible, but they tend to be more timing oriented. Okay, good question. Anybody else? There's nothing worse than performance bugs, by the way. So you think you got this perfect thing working and it always gives you the right answer, but sometimes it takes 12 hours to run when it's supposed to take 2 minutes, you know. That's a different kind of bug you can run into with concurrent threads. Okay, so today we're going to talk about some concurrency examples. We're going to try to really hammer home why you need synchronization to start with and give you some examples of valid synchronization as well. The reason I want to start with some concurrency examples is to really give you a flavor for why it's useful to have concurrency. Okay, now before we go there entirely, let's talk about this a little more. Is any program truly independent? Okay, and I was trying to indicate to you that perhaps it's not. File systems shared, operating systems resources are shared. Great example here is buggy device driver causes thread A to, something that thread A does with that device driver causes B to crash. And this happens to you probably more than you'd like to have happen. And reproducibility is pretty important, so I gave you this example at the very end of the evil C compiler that modifies things behind your back and only gives you correct code when you put debugging in, and when you remove the debugging information, it gives you bad code. Okay, now hopefully that doesn't happen too often, but this would be your good mental model of a very bad, non-reproducible scenario. Here's an example of something that unfortunately is very similar, which is, on the flip side, you put in your debugging statements, and as a result of the debugging statements, you're overflowing your stacks, and you're getting even worse behavior than what you were setting out to debug. Okay, so everybody likes to say, yeah, put in printfs. Well, maybe that the printfs screw things up. Keep that in mind, okay? This is why Heisenbug is so appropriate here, because you go to measure the state and you change the system. So non-deterministic errors and non-reproducible errors are a time-honored tradition in operating systems. You go back, original Unix had a whole bunch of them. I told you briefly about how the OS 360 basically had a bunch of anomalous program reports that were out. So there was 1,000 bugs that had weird things going with them when they released it. Okay, and you know that this happens all the time with your operating systems now too. So why should we allow the cooperating threads? And people cooperate. Why do they cooperate? Well, because hopefully you get more out of the cooperation than not. Hopefully, and you can imagine how many times have you tried to get a group of people together to do something and the thing you were intending definitely did not happen. Anybody? Have a bunch of friends together or something, you were intending to do one thing and it didn't happen that way? Oh, I see. You guys are much better at social interaction now than when I was going through school. So let's look at some advantages here, though. So sharing of resources is useful. One computer, many users. One bank balance, many ATMs. Okay? Embedded systems. Maybe you want to build a robot and coordinate both the arm and the hand together, right? Those are two things that are potentially independent, but you'd like them to coordinate in order to actually work properly. So sharing of resources is one. Another one is speed up. We've been talking about multi-core throughout this class so far, and if you can have multiple threads doing something, or multiple CPUs in this case, then maybe it goes faster. Okay, maybe. There is a standard kind of joke about parallel code, by the way, which is if it takes one person 60 seconds to dig a post hole, so there are these little devices you stick in the ground and you go like this and you get a hole for a post when you're done, then clearly it takes 60 people 1 second to dig a post hole, correct? Okay, you can see the problem there, right? There's some overhead issues. But in theory, there might be some speed up advantage. Another can actually be modularity, and this is one that is often not thought about. But for instance, if you take a look at a typical compiler that you might have in a Unix system, it's often divided into a series of phases, like the CPU processor or a couple of C passes, maybe an assembler and a loader. And each of these things are separate processes that kind of forward their results to each other in a pipe sort of fashion. And you might say that the reason for doing that is it's faster, and maybe that's true on a many core under some circumstances, but the more compelling reason for dividing things up like this is modularity, so that the assembler is thinking only about assembling and the loader is about loading. Okay, so this is in a case where cooperating threads are actually giving you some sort of correctness advantage, assuming you don't screw up the synchronization. Okay. Questions? So are you guys willing to give me the benefit of the doubt that perhaps cooperating threads might be useful under some circumstances? Okay, have I qualified that enough? How many people are willing to give me the benefit of the doubt here? Okay, good, good. Now, so let's take a look at one example here. So you got a web server, and you have 1 million people in the world all want to look at your website because clearly it's a very interesting blog of your life. And you might decide to speed this up a little bit with the following. Okay, so you might say, well, for each connection that's coming in, accept it, and then fork off a thread to service that connection. Okay, now, can somebody give me an example of why we might want to do this instead of the obvious simple thing of, for every connection, process the connection, then go back and grab the next connection? Why? Yeah. Might take a while to process the connection. Why? So that's an interest. So is it the processing that you might want to try to overlap here? Now again, you got to go back. Let's go back to a single processor in the system for a moment. So maybe not processor, but what? Network, memory, maybe disk. Yeah, go ahead.
Those network protocols involve a lot of waiting, especially over the internet, so we can do this process.
Yeah, so waiting for I/O basically is what we're really talking about here, is the big advantage. Okay. Now, so the advantage of this threaded version, you can share files. So by the way, these are threads in a process, right? So the process has the address space. Multiple threads can share the files. Maybe the results of CGI scripts can be cached if you're careful. That's a little tricky to do correctly. And threads are much cheaper to create than processes, so probably you'd want to use threads here. You wouldn't want to be creating a new process for every incoming connection. Although, by the way, early web servers did that, but that's very expensive. Okay? What's the disadvantage? Well, if too many requests come in at once, what happens here? Yep. You create lots of threads and then? Yeah, you got a problem because you've got more overhead than real computation, right? You got 1 million threads going simultaneously. The only thing you're doing is switching all the time. Okay? This is what's often called the Slashdot effect. Are you guys fans of Slashdot? Okay. So, the problem with something extremely popular is you get what's actually called a flash crowd, where suddenly everybody comes in simultaneously and the server gets completely overloaded. And this kind of a multi-threaded version probably might even crash the server because it's overusing resources. Okay, it shouldn't crash the server because it's running at user level. I'm just saying it might with high probability under certain circumstances. Okay, so what's another option? We could do something called a thread pool. So the problem with the previous version is the unbounded thread problem. And so what do? We bound the threads. Okay, so we say, well, instead we allocate a pool of threads. And that's the maximum level of multi-programming we want going on at any time, 10, 20, whatever the number is. Okay, and so here would be our basic example. So this little petri dish here is all the threads, and there's a queue on the input. And the idea is that every request that comes in gets put in the queue, and there's a finite number of threads here running, and they go and grab a request off the queue, they do something with it, finish it, grab the next request. And we only have a fixed number of things actually running in parallel at any time. Okay? So the master thread might do something like this. Allocate a bunch of threads, okay, and the queue. And while true, it accepts a new connection and queues it on the queue, wakes up the queue. We'll talk about this when we really get into monitors, probably on Monday. And then repeat. And so basically the master thread is not actually processing anything. All it's doing is grabbing connections and putting them on the queue, and if it turns out there's a free thread that's sleeping, it'll wake it up. That's all that it does. What does the thread pool do? Well, each one of those threads goes in an infinite loop here that says, well, can I dequeue something? If it's null, I'm going to go to sleep on the queue. Otherwise, I'm going to service the web page, go back again. And this little thing about sleeping on the queue is exactly the thing that this wake up is going to deal with. So if there's anybody sleeping, we'll wake them up when new things come in. Okay? Does that seem pretty clear to everybody? Questions? Now notice I just subtly introduced a bunch of synchronization here, right? So for instance, somehow we're going to in-queue stuff on the queue and dequeue stuff from the queue simultaneously. We better make sure that the two threads, both one in-queuing and one dequeuing at the same time, don't mess up the queue. Okay, yeah, question? No, con stands for connection here. Nope, not yet condition variable, but that's a good guess. In fact, you could build this in condition variable style quite easily. Okay, and the other thing, of course, is this notion of sleeping on some queue and waking up people sleeping on the queue. Okay, does this idea make sense to everybody? So thread pool is a pretty simple technique, but it lets us get by the unbounded parallelism problem while at the same time having the advantage of more than one thread. Okay. Administrivia. Well, the wait list is empty. Those of you that are in the class outlasted the wait list. At the very end, we were able to put the last person who was on the wait list into the class. So anybody who was here as of early this morning on the wait list, you're now in the class. There was only one person left at that point. So no longer an issue there. Now those of you that made it into the class are going to do extraordinarily well, right? This is going to be the best term ever. Yes, because you're all motivated. You should really be working on the first project if you're not. Okay? I won't even ask who hasn't started working on the first project because you'll be shunned and embarrassed and everybody will throw stuff on you. But if you would have raised your hand and I asked you about the first project, and you would have raised it because you hadn't started yet, you should really start immediately after class. Okay? First design documents actually due Monday at midnight, and normally in this class, design documents are going to be due on Friday, which would have been this Friday, except for the fact that there's some material in Monday's lecture which might be useful to you because there'll be a specific example of monitor style using the reader-writer queue that might help you. Say again? However, there's only a few hours between the end of class and that section. So I would suggest that what you ought to do is also be reading your book and talking to your TAs and go to section on Friday and so on. Okay? Don't assume that you're going to get all the information you need on Monday and suddenly, be done. Okay? The other problem with Monday is that I remember I said next Wednesday, a week from this Wednesday, I might not be here. It turns out it looks like it's going to be next Monday. So I may actually have Eric Brewer come in here on next Monday. We'll see. Okay. Design document. So what is a design document? So the thing a design document is not a bunch of code. Okay, so if you actually give us code with semicolons and stuff in it, maybe we'll give you a 0 on your design document. Okay, that might be a little harsh, but you should think along those lines. What a design document is supposed to be is it's supposed to be a description of your design. What is the motivation? What's the high-level ideas? Okay, and you could use pseudocode sparingly, but do not use full code. So there shouldn't be actual Java syntax with variables from nachos in there, and it shouldn't be compilable. Okay, it should be a document where you're describing your design. And an important inclusion there has got to be your testing methodology. So they talked a little bit about testing on Friday, I think, in section, and they're going to be talking more throughout the term. But bottom line here is not only you're going to tell us what your design is, but tell us how you think you're going to test it. Okay, and this, you don't have to say, well, first I'm going to put a 1 into A and try it, and then I'm going to put a 0 there, and then I'm going to try pi in fixed point to 5 decimal places. No. But give us, what is your methodology? How are you tackling your bugs? What are you going to do a wrapper around that? I think we're going to try to make JUnit available, which is a unit testing facility for Java. You can use that as a possibility. We'll talk more about testing as time goes on. Yeah, go ahead. You won't necessarily be submitting your test code, although you could, as part of your final submission. It certainly won't be the design document as a document. Yeah.
Formatting, is there an example as to what format you would like, or is there an example design document?
Yeah, I believe there's an example up on the website. But one thing if there isn't, I'll make sure that there is. But one thing I want to point out is this is a document, so we want PDF. So you guys will be maybe writing it in your favorite word processor, TROF. Actually, that's a joke because you guys don't know what TROF is, but Word or some Apple thing or LaTeX, whatever. But you're going to produce an actual document that reads with English in it. Okay, Okay. All right. Think of this as something you'd actually submit to your boss to describe your design, and the reason is that following that. Following that, you're actually going to be doing design reviews next week. Okay, so that's another thing that's going to happen. You're going to have to sign up for those. Normally, I'll get to your question in just a second. Normally, your design reviews are going to be on Monday and Tuesday because you will have submitted on Friday. Next week's a little weird, so you're going to have to negotiate with your TAs. I think they're going to try to do them Tuesday, Wednesday. But okay, question.
Could you clarify about grading your methodology for testing? How will it be graded?
So the way it'd be graded is, have you clearly thought through the test cases and vulnerabilities in your code? Have you described it cleanly? Does it look like you're really on track to having a coverage of testing, or did you just sort of say, I'm going to put a 1 and a 0 in there and see what happens? Okay. I mean, if you're going to say you put a 1 and a 0 in there, I shouldn't exclude that because that may actually be true in some circumstance. But explain why. What is that giving you, other than the 20th digit of pi or something? Any other question? Okay. We'll be a little bit lenient at the beginning and the first design doc, but assume that you're submitting this to your boss. Okay, and it's got to read well. I know that writing English is not something that we do as engineers, but let's try. If you need to know more about synchronization, there's lots of stuff. There's chapter 6 in your book. Make sure to start reading about monitors. Go to section on Friday. Come here on next Wednesday to class. Of course, you all do anyway, because we're going to talk a lot about synchronization then. We're going to talk about it today. Okay. I think that's all the administrivia. Yeah? AutoGrader won't go up until certainly after the design reviews. So the AutoGrader right now is kind of a mystery to most of you, unless you've talked to friends who've taken the class. But basically, the AutoGrader will be a methodology mechanism for you to submit sample solutions to see how you do. And it's going to be very much run on a batch standpoint. So in the early parts of code time, like first half week or more, it's going to be every 4 hours or something like that. So you can't just keep submitting. So your debugging and testing methodology needs to be outside the AutoGrader. Did you get that? Outside. Okay. Toward the end, we'll run it more frequently. I do promise that. Toward the end of each lab. Okay, any other administrivia questions? Everybody in a group? Yes? Yes? Everybody in a group? Good, good. Okay. Everybody in a group that's more than 3? Good. Okay. So let's talk about synchronization now in more detail. So here's a bank server. Okay, now these are actually ATM machines, even though they sort of look like phones. Use your imagination. So notice that there's some central bank computer somewhere, and all of these ATMs are basically putting in requests for money and getting requests out, and somehow you've got to let them work in parallel without corrupting the database. So examples of corruption would be handing out $1 billion to somebody at an ATM. Okay, now that might be a good, might be a good payday for the moment until they look at the film and figure out who you are, but it's sort of bad for the bank. Okay. Other things is you deposit your money and the bank forgets you deposited it. That would be another bad thing. Okay. And so somehow we've got to make this work. And this is going to be the first case where concurrency really comes home and looks pretty obvious. So let's start with a simple version of this idea. So suppose we did this. The bank server runs this infinite loop that receives a request, which includes what operation you want to do, maybe the account ID and how much you want to deal with, processes the request, goes back, does the next one. Okay, so what's great about this code is it's serial, it's easy to look at, it's easy to understand, and you're going to annoy ATM customers all over the world. Okay, because each one has to wait for somebody else for a long time, probably. Now, and of course, what do we do when we process the request? Well, we might say, gee, if the operation is deposit, then we deposit some money into the account. Otherwise, we do stuff, so on and so forth. Okay, so this is pretty easy. And what does deposit do? Well, it might say, get the account out of the database, look at the balance, add, suppose we're doing deposit, add that amount to your balance, store the account back in the database. Okay, and notice how this reading might use disk I/O depending on, I suppose if you're at the ATM continuously doing transactions, maybe they actually cache your account, but that's unlikely. But certainly writing back is going to involve disk I/O. And how do we speed this up? Okay, the most important thing is clearly going to be having more than one request going on at once. Okay? And there's actually a couple of ways we could do this. I'm going to show you an event-driven technique, which we're not going to focus on much in the class because it's actually pretty hard to get right. And then we're going to show you how to use multiple threads. Okay, so that's our goal. Are there any questions about the example? All right. So suppose we only have one CPU. And you still want to overlap I/O with computation. Now, I didn't point out the red in the way that I wanted to. See, this may use disk I/O, involves disk I/O. These are where we're going to slow things up for sure, because when you go out to the disk, it takes time. And when you write to the disk, it takes time. Does anybody know a good rule of thumb for how many CPU instructions are probably involved in a disk seek?
Depends on the disk.
Okay, so it depends, obviously. But give me an order of magnitude. Anybody? Yeah. Okay, it's a little worse than 100,000. We'll say 1 million.
Well, it could be 100,000 installed state. They're at the lower latency.
Yeah, it could be. Let's use 1 million for now, though. Okay, so 1 million instructions is a lot. Okay, maybe 100,000 under a lower bound, but unfortunately, solid state is not big enough to deal with. A bank isn't going to be able to deal with solid state. Too expensive. So. If there's 1 million instructions that could be involved in each of these disk I/Os, you can see that we're losing a lot of opportunity to overlap here because we're going off to the disk. Okay, so the first thing that we want to try to do is overlap that disk I/O with the actual computation. And if we're not going to use threads, then we have to do something like the following. Okay, now this is may take a few moments to get here, but if you notice, we go into a loop and we sort of say, well, grab the next event, which is going to be on an event queue. If the event is a request coming in, start the request. If the event is the account's available, continue the request. Otherwise, if the event is the account stored, finish the request. Now, you got to look back here for a moment, and I'm assuming that the only long latency things, which is kind of a lie here, but just for our example, are the red things. So we assume that when we receive a request, we can rush our way through until we get to the point where we might have to do disk I/O. Okay, and that's the point at which we might want to stall to deal with the disk. And so what we'd like to do is have the first event be we receive stuff, we rush up to this point, then we put this on the event queue again, and when the disk comes back, the I/O comes back, this guy's ready on the event queue, then we rush our way to here, we put the thing back on the event queue. When this disk I/O is done, we rush to be finished. Okay, so I've just divided this code into 3 phases, which are that are split up by long latency effects, and then our code kind of looks like this. Right? It's sort of, our event queue has pieces of ATM requests, both the starts, the middles, and the ends of the ATM requests. And every time each one of these guys here, okay, like start on request, rushes up to the point at which it's going to do some stuff on the disk, and then it puts that package onto the event queue, starts the disk I/O, grabs the next event. Okay? Everybody with me? Now, how many people think this seems like a very hard way to do this kind of code? Okay. Does this look natural and easy to anybody? Okay, we got one person in the crowd. There's always one. Now, what if we miss something? Like, for instance, there's some blocking I/O step in the middle of start on request that we forgot to see. And as a result, we're rushing through, but our events aren't divided up in a fine enough grain. And as a result, we rush to that point, put the whole system to sleep, and now nobody's getting processed. Wake up, start again. Okay, so we haven't divided our events up finely enough, and suddenly this thing performs really badly. It's back to what we got with our single non-multiplexed CPU. So you can imagine you have to split your code into hundreds of pieces. Okay, maybe that's not desirable. Question, yeah.
It's true that lots of UI use this technology.
Yeah.
Why do they choose it? Especially like a web browser, for example, it's so good at the queue of any events.
So the truth of the matter is, which was pointed out here, that in fact this technique is used in a lot of graphical programming. And the reason it's done this way is the graphical programming model is so well-defined and constrained that they can basically do this division. They can kind of figure out where the event boundaries are. And they can do it once for everybody that uses the windowing system. Okay, the way I've described it here, it's kind of like, well, as a programmer, you personally have to come up with every divide point for every new program, and it's a long, painful thing. For a windowing programming environment, it's kind of like somebody does that for you once, and then everybody uses it. And in fact, this event queue is in the middle of the Windows system and so on, X, Windows. And you have one thread typically on that, but then the rest of the system is often multi-threaded. So it's only the graphical piece where somebody spent the time to figure it out. So it's one of these things where spending the time might be worthwhile. Yeah?
If this server is single-threaded, then who's delivering the events?
So the events are actually potentially, what I haven't shown you here is you would actually poll the input port as well to look for new events. Okay, so you potentially have an event queue, plus you could poll and say, oh, look, there's a new thing coming in off the I/O queue. I'll put that on the event queue and keep going. So yeah, this is only part of how to do this. You can see that it could get arbitrarily complicated quickly, but it's very efficient, by the way. If you can do this well, this does not have the overhead of multiple threads going through switch, because there's only one thread. Okay, but you have to put a lot of work into it. Okay, I'm going to leave this example now unless there's any other questions, because we're going to go to the more mundane threaded version of something like this. which unfortunately has different set of problems than this one does. Okay, questions? All right, good. So can threads make this easier? Well, threads can kind of overlap I/O and computation without deconstructing the code. So you could kind of view what I did there. You take the request comes in, it looks up the account, then it does some stuff, it stores back the data. That's like an obvious thread of control, and what we did was we deconstructed it into pieces and put it on an event queue earlier. And with threads, we just keep that obvious pathway there. So we have one thread per request, and the request proceeds to completion, and it goes to sleep if necessary. So the fact that every request gets a thread means that there may be many threads going through this deposit routine, which is going to cause problems we'll get to in a second. But if this happens to have disk I/O and that one thread for the person in Beijing making an ATM withdrawal happens to go to sleep, it's okay because there's another thread that's on the ready queue ready to run. And so we don't have to overlap I/O explicitly in the code because it happens as a side effect of using threads. Okay, do I have to say that again, or did everybody kind of catch that? As a side effect of us dividing into multiple threads, what we said essentially is that if one of the threads blocks to go to sleep on I/O, it's okay because there's another thread that can immediately take up the CPU. Okay, and if it turns out there isn't another thread laying around, then we couldn't have gotten parallelism out of the event model either. Right? So this thing kind of gives you the parallelism exactly when you need it. Of course, with the caveat that if you have too many threads, as we mentioned with the thread pool, you got a mess. So unfortunately, as nice as the threading model might be for a programmer, it's got some problems to it. Like, for instance, look at this. Somebody explained to me, so here we have thread 1 is in the deposit routine and thread 2 is in the deposit routine. And I'm actually showing you sort of pseudo-assembly language here for this middle statement here, account balance plus equal amount. So how do we actually do that? We load the balance into a register, we add the amount to it, we store the balance back out into the structure. Okay, so that basically, this single piece of C or whatever language you're working with actually comes into 3 instructions. Now, could somebody tell me what the unfortunate side effect of this particular interleaving is? Yes?
So you read the account balance in one thread, and then thread 2 actually change that balance, but thread 1 is still the total account balance.
Yeah. So this is your mom is putting $1,000 into your account, you're depositing $10. So you're on thread 1, your mom's depositing $1,000, and somehow when you're done, you've got $10. Okay, why is this? Well, this is because, this particular interleaving that the dispatcher chose is very bad. Okay, because what it did is this particular 3 instruction sequence needs to be atomic. It needs to be never interrupted, but instead what happened here is we started on one thread, we switched over to the other one, and when we came back we completely undid what thread 2 did. Okay, any questions on this example? Okay, now for those of you that have parents depositing money remotely probably want this fixed, right? Maybe even those that think that might happen at some point in the future. So how do we fix this?
Make it a critical section so they can't interrupt it.
Yeah, we got to somehow make this an unbreakable critical section, somehow. Okay, so we're going to have to somehow put these two things together. Now let me make sure that we review a couple of stuff. Remember I said malicious scheduler. So what does it mean to run 2 threads concurrently? It means essentially scheduler can run in any order it wants, which means it's probably choose an order that's bad for you. So for instance, if you have multiple threads, then you've got the 2 ATM or 3 ATM things are really going in parallel. Okay, so then you know that's going to happen under some case. Here, if you actually have only one CPU, then this particular example where the dispatcher chooses thread A, then B, then C, or the scheduler, that works, right? Because we never break up instructions, whereas this interleaving might break up instructions. So the point here is when you're looking at these parallel cases, you've got to somehow mentally simulate the worst scenario. Think to yourself, how could this really go wrong? So that's the first thing you're going to have to get used to. Okay, because, you know, in this case, you have to say, well, what could go wrong here? Well, this is pretty wrong, right? But how do you figure this out? Well, you'd have to figure this out by thinking it through. And by the way, this is where you have to tune your intuitions and figure out how to come up with these weird cases. Okay, and I can only guide you in two things. One, start to help you figure out how to think about weird cases so you can come up with them. And two, I can give you some programming methodologies that are less likely to have this kind of problem. Those are pretty much the only two things that I can do, but I'll do my best. Okay? All right. The other thing to remember is, of course, hyperthreading also gives us kind of this example, even though there's only one CPU. So the problem is really at the lowest level here. So most of the time, threads are working on separate data, so the scheduling doesn't matter. So for instance, here, suppose that thread A says x equal 1 and thread B says y equal 1. Is that a problem? Okay, it doesn't matter whether they do it at the same time or different times or before or after. Why? The data is different. Okay, so this is an example where the interleaving of the threads are not sharing data, and so it doesn't matter. This one's a little trickier, right? So what are the possible values of x when these two threads are done?
13, 3, or 5.
Looking at my slides, of course. Don't you just gave that up? Okay, good, good, good. 13, 3, or 5. Can anybody see why? Well, suppose that thread A runs to completion, x equals 1, and then y started out at something here. Okay, initially y is 12, so if x equals 1, and then x equals 13, right? And then thread B gets to run and nothing happens. Or we start running this guy, and then we go over and y equals 2, and then y equals 4, and then we come over here, and then x equals 5, and so on. So you can mentally simulate the different options, right? Okay, and so you get basically all of those. Everybody with me? And of course here, what are the possible values of x? Is this a trick question? What are possible values of x here? 1 and 2. Can anybody argue why it might be 3?
One resets half of it, and then the other one sets the other.
Very good. So if we have a non-atomic load store where some bits can be set for others, like, say, a serial processor, it's possibly the case where thread A starts writing bits and then B writes some bits and you interleave, and maybe you could get 3 out of it. Now, fortunately, none of the processors you guys are going to use in this class will ever do that. And the reason is that loads and stores by themselves are atomic at the one-word level. Okay, so basically what you will see is either x is 1 or 2. You can't tell which, but those are all the options. You can't really interleave bits. There are certain types of hardware, by the way, that might be writing things out in serial, and that could be a problem. But that's a pretty esoteric piece of hardware.
Well, floating point, if you have like a 4.
Okay, so the example that's brought up here, which is good, which I will mention, is if you have floating point that's actually two 32-bit words, it's possible you could run into this problem because half of the floating point gets written and then the other half. Yeah, question in the back. Okay, yeah, so that's a case where we don't necessarily have an atomic store, but that's bigger than a single word in that case. The floating point problem could be a problem if you use a load or store for floating point that's not atomic. You got to be careful. And it's doing 64 bits at a time. Yes. Okay. Good. Any other questions? Okay, so what I want to do is let's take a break for about 3 minutes, and we'll come back and we'll talk about atomic operations, and then I want to make sure that we get through the got milk example, which is the key for the lecture. Okay, let's start sitting down. So, I want to introduce some terminology here. So, to understand concurrent programs, we need to know what the underlying indivisible operations are. So, an atomic operation is going to be particularly useful for us to know. It's basically something that's indivisible, which means there's no way for any other code to get in the middle of this operation. So a good example of what we'd like to be atomic is what we were giving previous in that bank example, the load, modify, store. We'd like that to be an atomic operation so that there's no way to get any interleaving there. Right? So if we could make that load, modify, store be atomic, then we don't have the problem of things not quite working properly. Okay, is everybody with me on that? So most machines have atomic memory operations, loads and stores. Okay, so that example that I gave you with 3 is basically pretty much doesn't happen much. Now a floating point could be an example of that with 64 bits using 2 32-bit loads or stores, but mostly you don't have to worry about this. Many instructions are potentially not atomic, like for instance, here I mentioned the floating point. For instance, the VAX in IBM 360 and x86 all have string copy operations. And the problem with a string copy operation is you're asking in a single instruction to do a whole bunch of stuff. You know, and if that instruction gets interrupted in some way, then it's possible to get half of that instruction done or whatever. So you always want to ask yourself, what are the atomic operations in your system? And for the next till the end of the lecture, we're going to certainly assume that 32-bit loads and stores are atomic. And we're going to ask ourselves, can we program with 32-bit load stores being atomic, and those are our only atomic operations? Okay, so for instance, that 3 load, modify, store example, we'd have to build something to allow us to turn that into an atomic operation, because by definition, for this lecture, it's not. Okay, so when you start doing your design docs, one of the things you need to think about is what is the correctness operations, or what are the correctness criteria for whatever it is you're designing. And one of them will be about the fact that threaded programs, the 2 different threads, ought to be able to interleave in any valid way, and you still get the right answer. Okay, and I want to tell you about a couple of examples where that didn't happen. So one of them is the Therac 25. How many people have heard about this? Good, they tell you about this one. This is bad, right? So what's the Therac 25? So this was a radiation therapy machine, and basically it gave software control of the distribution of electrons or X-rays to a patient. Okay, that seemed like a good idea, except for the fact that by making the Therac 25 over the 20, I guess, or whatever, they actually removed a bunch of hardware interlocks and replaced them with software, because of course software doesn't ever have bugs in it, right? Now the problem is bugs in the software killed a bunch of patients. Okay, oops is exactly right. What happened is they gave them way too much dosage of radiation, and as a result they had some very bad symptoms for a month or 2, and then the worst symptom was they were not alive afterwards. So this, what's worse about this is this was a series of race conditions in the software. Okay, they didn't design the software well, and as a result caused these race conditions. And a particular one that I think is amazing here is, this is a quote from a paper, by the way, I put up for reading on the lecture page. They determined that data entry speed during editing was the key factor in producing the error condition. If the prescription data was edited at a fast pace, the overdose occurred. So this is a great error, right? If you've got an operator who really knows the machine well and is typing fast, then they're more likely to kill you as a result. Okay, so that's a very bad synchronization bug. Now, I hope you never get in a situation where your software bugs can cause a problem, but this is a good example of such a thing. The space shuttle is another thing that was a little less serious, but it was actually aborted, the original launch, 20 minutes before the scheduled launch. And the reason is the following. So when they designed the shuttle, they tried to be really, really, really redundant. So they actually had 5 computers. So 4 of them all worked together doing the same thing, voting. Okay, and a 5th one was designed in a completely different way. So this was kind of an asynchronous set of 4 systems that were voting together. Here is the a synchronous system, and what would happen is there'd be this continuous comparison, and if there was ever a failure to compare in here, then you'd actually throw out the one that didn't get voted, and you'd still have 3 that were working well, and then this backup comparison would actually be hopefully continuously synchronized so that if things really went well, this guy was always ready to go. Okay, and why did this happen, that the things were aborted? Well, because the BFS disagreed with the set of 4. Said, well, they got the wrong answer. Now, it did it 1 out of 67 times, which of course included the one time that they were on the shuttle launch ready to go. That's a little unfortunate. Okay, now what it turned out here was this was purely a synchronization bug in the part that was supposed to keep the state in sync. It wasn't actually a bug in the system. So this would have flown well, except for the fact that their backup system that was supposed to make sure that it flew well said it couldn't fly. Did you catch that? So there's actually a bug in the initialization code that caused this, and it took them a long time to debug this. There's also a paper about this up on your readings. If you want to see some, somewhat notorious synchronization bugs, both of these are described on the readout, the lecture page. Okay? And they actually didn't find this during design. It only happened when they tried to launch. Yeah, question?
For many of these embedded systems, verification software, especially for like airplanes and things like that. So,
well, they spent a long time developing the verification software to try to catch these things, but this was a good example where they had extensive verification software and it still didn't catch the problem. So, you never run as many cycles as the first time you boot a new system, because simulation is just way too slow. So here's another example. So then we're going to actually try to build atomic operations. But suppose A and B compete with each other. One tries to increment the shared counter, the other tries to decrement it. Okay? And it looks like this. Thread A sets I to 0. It's busy incrementing. If it ever gets to 10, it wins. B decrements. If it ever gets to minus 10, it wins. Now, who wins? Well, assuming that memory loads and stores are atomic, but incrementing and decrementing are not, who wins? Could be anyone. Is it guaranteed that somebody wins? No. Right? Because, they're basically busy undoing each other all the time. And that's not just because one's incrementing and one's decrementing. That would be nice if that was the chaos we're worrying about. The problem here is that we can actually have one of them undoing what another one just did in a weird way. Okay? So this is very bad programming style. And of course, we can simulate this. You ready? Here we go. Thread A and B. Okay, so A gets the load. Okay, B gets the load. All right, A's off to an early start. B says, we better go fast. So now A adds 1. Now B subtracts 1. A stores 1, right? Because it just added 1 to 0. B stores minus 1. A's like, wait, I could have sworn I just put a 1 there. Okay, can this happen on a uniprocessor, not a multiprocessor? Sure. It's very unlikely, by the way, that the scheduler is going to switch on a per instruction basis like this. But certainly with a hyper-threaded machine, it could. Okay, and you need to think as if this could happen when you're evaluating your code.
Craig one did it was finally multi-thread.
Yeah, so anything that's got fine multi-threading, I mean, the hyper-threading I told you is a great example of that, could do this for sure. But you should always think as if it's happening. Okay, here we go. Let's see if we can make bugs like this go away by producing atomic sections when we only have load and store are atomic. Okay, and I hope to convince you afterwards that while it's possible, you don't ever want to actually have to do it. So our motivation here is going to be what I call the too much milk motivation. Okay, so you're living with your roommate. And the great thing about the operating systems domain is you can often come up with real life examples to illustrate what's going on. So here we go. You and your roommate share a refrigerator, and it's important that the milk never runs out. Okay, so person A gets home from class at 3, looks in the fridge, finds out you're out of milk. They leave for the store. Meanwhile, person B comes home, looks in the fridge, finds out you're out of milk. They leave for the store. Person A goes and buys the milk. Okay, arrives home, puts the milk away. B arrives at the store, buys milk, comes home, and now you got too much milk. Now, there's some assumptions in this, like, you know, your roommate likes to go, both of you guys like to go clockwise to the store and home or something. So that, okay. And now the question is, can we fix this problem with just loads and stores? Okay. Now, some definitions. So synchronization, which was the title of this lecture, I never actually defined, but it's going to be using atomic operations to ensure that threads cooperate properly and give you correct behavior. And again, loads and stores are the only atomic ones. And we're going to show that it's really hard to build anything useful with only atomic reads and writes. Mutual exclusion is ensuring that only one thread is allowed to do a particular critical thing at a time. So a good example in the milk analogy is that only one of you can actually be in the purchasing milk scenario at once. That would be something we'd want a mutual exclusion on. Okay? And then finally, a critical section is the thing you do mutual exclusion on. It's a piece of code that only one thread can execute at once. Okay? And so the critical thread section is the result of mutual exclusion. And perhaps mutual exclusion and critical section are different ways of describing the same thing. Okay? Now, let's start with what's a lock. Okay, so hopefully everybody here knows what a lock is on a door, right? You got a key, you open it up, you go into the door. What is it in software? Well, it's got the same idea. It's going to prevent someone from doing something, where now the someones are threads, okay, to do a little morphizing. So what we're going to do is we're going to lock before entering a critical section and before accessing shared data, and then we'll unlock when we're done. And by doing that, the shared data will be protected so that only one thread can mess with the shared data at once. Okay? And if the data is locked and you go to try to do lock, what happens? You wait. And believe it or not, the most important idea in all of synchronization is waiting. The way we fix these weird interleaving problems is we make somebody wait so the interleaving goes away. Okay, so waiting is actually the crucial idea here. And it's going to be a question later of how we make sure that the waiting isn't done wasting time. Okay, we're going to try to avoid busy waiting, but for now, waiting is most important. So how do we fix the milk problem? We put a key on the refrigerator, right? You come home, you unlock the fridge, or you come home, you look, you see there's no milk, you lock the fridge, you take the key. You go to the store, you come back, you unlock the fridge, you put the milk in there. Okay, does this fix the too much milk problem? Yes, but unfortunately it probably pisses off your roommate. Because in some sense, this sort of fixes too much, right? This is the, the roommate only wants orange juice and you've just locked him out of the refrigerator. Okay, but it does fix the synchronization problem and you do make them wait. Okay. So how do we don't know how to make a lock yet either, so that's kind of another problem. I give you this abstract thing of locking up the refrigerator, but I don't know how to make it yet. So what are some correctness properties for this issue? So we want to make sure that we don't get non-deterministic behavior, and so we want to think through what we really want out of this. And one of them is, the reason we're going to do this, by the way, is that the impulse is to start coding. And let me just tell you, if you start writing code before you come up with your correctness properties, you will get bad code. Okay, because what's happened is you'll write something, it'll behave in a strange way, you'll tear your hair out. This happened to me a few years ago. And you'll never get it to work because you haven't thought it through. Okay, so think first, then code. Okay, all together now. Think first, then code. Very good. So what are the correctness properties for the milk example here, right? So never more than one person buys the milk. Okay, and someone always buys it if you need milk. So these seem like important correctness properties, right? And we're going to restrict ourselves to only atomic load and store operations as our building blocks. Okay, any questions on this before we go forward? By the way, these kind of correctness properties might be a great thing to put in your design document. For instance, what are the correctness properties you're shooting for? So here's solution number 1 to the too much milk problem. Use a note. Dear Frank, off buying milk. Miss you, back soon. Okay. You leave you leave a note before buying. It's kind of like a lock. You remove the note after buying. Don't buy a note, or you don't go buy if there's a note. Okay. So this seems like it's a good idea, right? So what's wrong with this solution? Yeah.
Well, if you leave a note, that the person can be writing when you check it. So if that's the case, then you'll see that's not there. You'll also leave a note, and the case will be.
Now, if you're doing this with an actual roommate, this probably will be fine. But let's take a look at what a computer might do, right? If there's no milk and there's no note, leave a note, buy milk, remove note, good to go. Okay? And the thing to note about here is, still too much milk, but only occasionally. Okay, so why is there only occasionally too much milk? Yeah.
Checks are not atomic.
Yeah. These checks here are not atomic because suppose that both of us check for there being no milk, and now, by the way, you have an invisible roommate, okay? And now you look and you see there's no note. Both of you see there's no note at the same time, and now both of you leave a note and head out to buy milk. Okay, so there is a synchronization condition built into this code that is a weird interleaving where things switch just at the wrong time. Right after you've looked through the conditions, you switch over to the other guy, they look through the conditions, they leave the note, you come back here, you leave the note, and now you're screwed up. Yeah, question? Is disabling interrupts atomic? So I think that's not the question you wanted. Is disabling interrupts a way to get atomic behavior? Was that what you were looking for? No, okay, so disabling interrupts is atomic. Maybe a better question would be if you disabled interrupts, did a bunch of stuff, re-enabled interrupts, would that give you atomicity? And the answer is often yes, but you can't do that at user level. We'll talk about that next time. Yeah?
What if you just put some money and how much it costs on the table? Somebody come and it's not going to take the money and leave.
The problem is that then your roommate takes your money and goes and buys beer or something. So the problem with this solution is the thread could get context switched. Not that that's better or worse than milk. Don't. The problem here is the weird context switching condition. Okay, so the solution actually, I would say, this solution makes the situation much worse. And the reason the solution is much worse is because it looks like it works fine most of the time. Right? And you only get this weird intermittent condition where it isn't fine. Okay, does everybody agree that that's probably worse? Because you run it, it looks great, and then 12 days later, it doesn't work, and the space shuttle crashes or something, right? So let's see if we can come up with, here's solution 1.5, okay? This one, basically, clearly the note doesn't block well enough, so let's try this by doing the note first. Okay? So the problem was we checked stuff and then left the note, so let's leave the note first and then check. Okay, what's the problem here? Okay, assuming that it's been a long day and you're kind of acting like an idiot, you put a note, you notice the note, you go away. Okay, so this particular solution is not great either, right? Because this is essentially, well, with humans probably nothing happens, but pretty much nobody buys milk. Okay? This is the Homer solution. Okay? So let's try multiple notes. So we label the notes, okay? You get green and your roommate gets blue or something. And now we leave a note before checking for the roommate's note. Does that sound like something we could do? Okay, so let's try that. So here we have, now we're going to start differentiating the threads. So thread A and B do different things. So thread A leaves note A, says if there isn't a note B, then we say if there's no milk, buy milk, and then remove note A, and thread B does the same thing. Okay? Does this work? I'm seeing people shake their head. Anybody want to actually tell me why it doesn't work?
A could leave a note, then B could leave a note, and then A could check for B's note.
Perfect, right? A leaves the note, B leaves the note. Nobody buys any milk. Okay? So this is possible for neither thread to buy milk. And now this is really improbable. And so this is one of those Heisenbugs, or it looks like it, that it's going to show up at the worst possible time. This one's even less likely than the previous one. Okay? So this is extremely insidious. And by the way, original versions of Unix had a number of these. Okay? Because this looks like great synchronization if you're not thinking carefully. I mean, this looks fine, right? Unless you're in the right mindset to really interleave. Does anybody understand why this is there anybody that's not clear yet why this doesn't work? Because if there is, there's probably somebody else that has the same question. Are we good? Okay, yeah, question, yeah. There, that's good. The designated milk buying car. Unfortunately, that's probably too expensive a solution for a typical student, but okay, that might work because that's an atomic car, sort of. I mean, that would be a solution here, but that's not quite where we're going here. All right, so this was the I'm not getting milk, you're getting milk. Okay, and what's kind of funny is this is actually a lockup that can be called starvation in reality, so I guess that works. Okay, are we ready for solution number 3? Here is another two-node solution. Now this is a little more complicated, so look at it carefully. Notice how thread A leaves node A, and then it says, well, if there is a node B, I'm going to wait. And then finally, if I'm going to check and see if there's no milk, buy milk, and exit. And then B doesn't quite do that. It just says leave a note. If there's no note for A, do it. Otherwise, don't do anything, and then remove my note. Okay, so you see how these are slightly asymmetric. They're not quite the same thing. Does this work? And if you say yes, you have to tell me why. And if you say no, you have to tell me why. Yeah? Yes with a caveat. Okay. Say again? Thread B is going to buy all the milk? Perhaps, although that depends on your arrival. Okay. Actually, I think probably it's more likely that A will buy milk than B. But so you think it works. Why does it work? Go ahead. Keep going. Yeah. Yeah, notice we've got some wait condition going on here, and we're trying to be a little bit clever about it. Like we leave our note, which is kind of like a promise to investigate, and as long as B has got a note up there, we don't really know what B is going to do. So we kind of stall until the note goes away, and then we buy the milk. Over here, we leave our note, and we can basically say, well, if we've gotten as far as leaving a note, then we know for a fact that either A is stalling in a loop or it hasn't gotten in here yet, so we can safely go through and buy milk and whatever, and by the time then we can remove the note, and A will check the condition, which may get updated by the time it looks at it, but we won't get any duplicate purchases going on. Okay? So both are basically guaranteeing, one, it's safe to buy, or other will buy and it's okay to quit. Those are kind of the two things we're looking for. Okay? Now, how many people are mildly uncomfortable declaring the solution successful? Okay, good. I mean, you know, I'll tell you it works, but you're going to stare at this. You should convince yourself. You don't have to do it in the next 5 minutes, but you should convince yourself this works. It's kind of, you know, it's basically an X, and if no node B, safe for A to buy. Otherwise, wait to find out what will happen. If no node A, safe for B to buy. Otherwise, A is either buying or waiting for B to quit. You can convince yourself of this, but boy, this is not something that you can clearly look at and say, yeah, obviously that works, right? You have to stare at it a while to be comfortable with it. So anything that requires you to stare at a while to be comfortable with is probably bad programming practice, whether or not it works. Because you may come up with this, right? You know, best things are always done in the shower. You're in the shower, you figure it out, you write it down, and the next day you can't remember why this works. Okay, that's bad programming style. Okay, so one thing we can say about this code is each chunk here is protecting a critical section. So basically, think of this part, leave node A while node B is an entry, and the remove node A is an exit, and this if no milk, buy milk is a critical section, and it's over here too, that we want to make sure only one of the people do at a time. We don't want any interleaving on the if no milk, buy milk critical section. Okay, so that's exactly what this is what we're protecting here. And solution number 3 works, but it's extremely unsatisfactory. It's complex. Come up with a generalization. Suppose you got 20 threads. Okay, that's an exercise for the reader. And another thing that's bad here is, well, A is waiting to see what happens with B's node. It's spinning. So it's busy waiting. So we're actually wasting CPU time here. And let me show you why this is insidious. Because if we say B left its node and was going to check the milk, then we switch over here and A leaves its node and it's busy spinning, saying, well, B has a node set. If there's only one CPU, then while we're spinning over here, we're not running through buying milk. Okay, so we're actually wasting CPU time that isn't helping us make any progress. So we know that we'll literally not make any progress until we switch back to B to make progress. So this is just bad programming style for many reasons. Okay? And there's a better way. And that better way is have the hardware provide better primitives. Okay, and I'm going to quickly show you a good solution here. And the solution is, suppose we have a lock. Well, I haven't told you how to do a lock, but suppose we do. Then we might have a lock acquire and release, which wait until lock is free, then grab, and lock release is unlock. But notice this wait here, I haven't specified, is it busy waiting or not? In fact, when we talk about a lock, usually what it means is you're actually put to sleep on an actual queue, and so you're not busy waiting. Okay, and so these are atomic operations. It's not possible for 2 folks to be in the middle of lock acquire at the same time. And here is our simple solution that works no matter how many roommates there are. They all try to acquire the milk lock. Then they say if no milk, buy milk, and then they release the milk lock. Okay? And what we notice is that if multiple roommates simultaneously try to go look about the milk, only one of them will get past acquire. The rest of them will be sleeping until the first one goes through the milk, buy milk, releases, and then the next one can go through and so on. And so we only have one going through the critical section. Okay, so once again, we have our critical section, which is the thing between acquire and release. And of course, you can make this even simpler. I suppose we should have started with this one if, you know, just buy ice cream. Doesn't matter if there's too much of that. Right? All right, so let's say in conclusion for now, concurrent threads are very useful abstraction, but they sort of introduce synchronization problems. So concurrency is a nice way to split up having multiple things going on at once, but now you got to be careful about what they cause in terms of correctness. And those problems all have to do with accessing shared data, and programs must be insensitive to arbitrary interleavings. You got to assume that the scheduler is going to try to screw you up. And so that involves A, thinking in the right way to imagine these interleavings, which you guys are getting good at, and the second is designing things in a way that are unlikely to have bad interleavings. That's what we'll talk about next time. And so the important concept was atomic operations, and we showed you how to basically use just loads and stores, but it's extremely complex. So next time we'll talk about better primitives, better atomic primitives. You guys have a great couple of days. We'll see you on Wednesday.